Okay, in this lesson, we're going to be talking a little bit more about complex numbers. And let's recall a little bit that we know or remember about them. Recall that complex numbers are written in this form, a plus bi, where a is the real part and bi is the imaginary part. So every complex number has the real and imaginary. Now, sometimes the real part might be a, sometimes the imaginary part, the real part might be 0, sometimes the imaginary part might be 0. A complex number can be represented by a point, a comma b, and graphed on a complex plane. The complex plane consists of a horizontal axis, just like an xy plane, except for now we have a real and an imaginary plane. So we have a real axis and we have an imaginary axis, and we're going to plot these numbers. Now, I want you to keep in mind that they're not points. These are still numbers. However, what we've done, if you remember the real number line, like 0, 1, 2, 3, -1, -2, -3, we plotted those numbers on that real number line. Like if I ask you to plot the number 2, you come over at 2 and you put a dot. That is this number line. So where are these numbers located? They're located above and below the real number line. So let's show you how to graph these. To plot the point for -5 plus 2i, you simply go to -5 on your real axis, 1, 2, 3, 4, 5, which is right here, and you're going to go up to 2 on your imaginary axis. This is the point, -5 plus 2i. It's located 2 units above the real number line. 1 minus 4i, simply go right 1 on the real axis and go down 1, 2, 3, 4. This is the point, 1 minus 4i. So super simple. Now, 3i is the same thing as 0 plus 3i, so it doesn't have a real part. So this is kind of like, I guess you could say, like a quadrantal angle. It's going to be located on your imaginary axis. So there's 3i. The next one, let's write them as a complex number. So we went over 1, 2, 3, 4. So 4 is our real value. And then we go up 1, 2, 3. So that'd be 4 plus 3i. Next one, we went over 1, 2, 3, 4, 5. So 5 is our real number. And then we went down 1 unit on our imaginary. So this would be 5 minus I. And the next one's a pure imaginary. We didn't go right or left any. We just went down 2. So this would be -2i. Okay, next up, absolute value. And remember that absolute value is the distance from 0. It says the absolute value of a complex number is its distance from 0 as well. To where if we're talking about real numbers, the absolute value of -3 is 3 because the distance from 0 to -3 is 3. Thus, the absolute value of a complex number can be found by using the Pythagorean theorem. If we're looking for the absolute value of this number right here, the absolute value is the distance from 0. And again, if the value, this is A or B and A, to find this absolute value, again, we can just simply do the Pythagorean theorem. The absolute value of an imaginary number z is going to equal the square root of a squared plus b squared. And again, this is simply Pythagorean theorem. So the absolute value of a plus 6i, you could look at the graph of that, go right a, go up 6. So here's the point. So if this is 8 and this is 6, you can do simply a squared plus b squared equals c squared. That's going to be 64. Well, the absolute value is going to be the square root of 64 plus 36, which is the square root of 100, or 10. And that is a triple. 8, 6, 10 is a triple. To find the absolute value here, it's going to be the square root of a squared, which is 9, plus b squared, that's -1, b squared, which is 1. You don't have to worry about the I. Please don't include the I. So the square root of 10 is going to be your root there. The next one, the square root, this is, again, absolute value. The square root of a squared would be 4, plus -11 squared is 121. So that's the square root of 125, which is going to be, let's simplify that. That's the square root of 25 times the square root of 5, which is 5 root 5. Okay, now we're going to tie all of this together and talk about the polar form of a complex number. Every complex number can be written in a polar form. It says, no, when written in polar form, r is called the modulus, theta is called the argument of a complex number. And here is your polar form. The polar form, or trigonometric form, sometimes it's called, of a complex number z, and remember that z is a plus bi normally, we're going to now write it like this. Z is going to equal r times the cosine of theta plus I sine theta. Where again, R is your modulus and theta is your argument. And here's how you find R and theta. We know that R is simply the absolute value z. They put R because it stands for radius, as it has in the last few lessons. So R is going to be simply the radius of your point. It's how far it is from the origin, which again is absolute value. And then finally, to find the theta, we're going to simply use, we know that tangent, if you're given a point, again, look at this. If we've got a point right here, well, how do you find this theta? You simply do, if this is your x value and this is your y value, or in the case that we did it, instead of x's and y's, we did a's and b's. If this is your a value and this is your b value, to find theta, you're going to do the tan of theta would be opposite over adjacent. That's it. It's simple trigonometry. So next up, number 10. It said write each complex number in polar form, and then let's graph it on the polar grid. So 4 minus 4i, if you were to, now this is no longer your r theta, or excuse me, this is no longer your real complex grid, it's now your r theta grid. So let's see if we can graph it here. Let's write it first off in polar form. So let's find our r. Which again is your modulus. R is simply the absolute value of that 4 minus 4i. To find the absolute value, do the square root of a squared plus b squared. That's going to be the square root of 32, which is 4 root 2. There's your modulus. Now to find your argument, to find your angle, we know that the tangent, and you can graph this. Here's the real imaginary plane. 4 minus 4i, you go out 4 and down 4. It's located somewhere down here. So let's kind of sketch that. So we went out 4 and we went down 4. So we're needing this angle now. The way that we're going to find that is we know the tangent of the angle is going to equal b over a, or y over x, however you want to remember it, which is 4 over 4. So which actually it's 4 over negative 4, because this went down 4, which is going to be a negative 1. So therefore, let's use our reference angle. I always like starting with my reference angle. The tangent of what is equal to positive 1, that is a 45-degree angle. So that's my reference. So this is a reference angle of 45, and that means that my theta is going to equal, you can do a negative 45, or we can use this angle, which is a 315-degree angle. And again, that's because my point lies in the fourth quadrant. So now let's just piece it all together. Your trig form, or your polar form, is equal to r cosine theta plus I sine theta. So you're going to do your modulus, which is 4 root 2, times the cosine of theta, which is 315, plus I sine 315. If you were to multiply this back out, you should get 4 minus 4i. So you have a radius of 4 root 2. You have an angle of 315 degrees. So we're going to go out 4 root 2, which is about, if you were to write that in decimal form, 5.7. So we're going to go out 5.7 and rotate 315 degrees. So 315. Now notice they've got all these in radians. So I should have probably, instead of 315, pi over 4 was my reference. 315 would be 7 pi over 4. So we're going to be located at 7 pi over 4, which is actually right here. That's 315 degrees. And we're going to go out a radius of 5.7. So here's 4. Here's 6, so 5.7 is going to be about right here, which is the exact same place that it would be if I went right 4 and down 4 on my real imaginary axis. Next one. Again, the first step is to find our modulus. We find the modulus by taking the absolute value of this. So we're going to do the square root of negative 7. The negative square root of 7 squared is going to be just 7. Plus the square root of 21 squared will be just 21. So your absolute value is going to be the square root of 28, which is 2 root 7. So there's your modulus, and that's going to be about, for when we graph it, I'm going to go ahead and write, that's about 5.3. Okay, now the argument. I know that the tangent, and let me go ahead and graph this in the real imaginary axis. I'm going to go left root 7 and up root 21. So somewhere up here, that doesn't have to be exact, but I know that my angle, that the tangent of my angle, excuse me, I've already written it over here, will equal opposite over adjacent, which is going to be root 21 over negative root 7. And again, if you want to forget completely about the whole negatives and positives and all that, and let's get a reference angle. The way we find a reference angle is by ignoring that negative and positive. And let's just say that the tangent is equal to root 21 over root 7, which is actually just root 3. And you know, we can actually find that. That's one of our exact ones. Our reference angle, I'm going to put REF because this is where I'm finding my reference. The tangent of a 60-degree angle is root 3. So therefore, that's my reference angle. So therefore, this angle must be 180 minus 60, which is 120 degrees. So my theta is going to be 120 degrees, which if we want that in radians, my reference angle is pi over 3. Let me try that again. Pi over 3, which is 60, so 120 would be 2 pi over 3. So that's my actual angle that's going to carry me to the second quadrant. So now we're ready to write our trig form. My imaginary complex number is equal to the modulus, which is 2 root 7, times the cosine of theta, which is 2 pi over 3, plus I sine theta, which was 2 pi over 3. So there is my trig form or polar form. So now let's actually graph it, and it should end up in the exact same place if I use my radius and my angle. My angle was a 2 pi over 3 angle, which we see is located right here. My radius was about 5.3. Each tick mark counts for 2, so I'm going to go out 2, 4, 5.3 should be about right in the middle, which is about right there. That's my point, negative root 7 plus I root 21. Next up, first step, find your modulus. We find our modulus by taking the absolute value. So we're going to do the square root of negative root 11 squared, which is 11, plus negative 8 squared, which is 64. So that's going to be the square root of 75, which is 5 root 3, which is going to be about, for whenever I graph it, 5 root 3 is going to be about 8.7. Okay, so there's your modulus. So now let's find your argument. We know that tangent is equal to b over a, so negative 8 over negative root 11. You do not have to worry about rationalizing this because we're fixing to turn it into a decimal anyway. I'm concerned with my reference angle. To worry about, or when you're looking for a reference angle, simply ignore the positives and negatives. And then you can use your reference angle to place it in the right quadrant because you already know a negative and then another negative would carry you left and then down, which means you're in the third quadrant. So you're looking for a third quadrant angle. So you're looking for an angle between 180 and 270. So let's use this 8 over root 11. Type it in, do the inverse tangent of that to find our angle. So we're going to do the inverse tan of 8 over root 11. So that means my reference angle, and I'm going to put it in blue here, my reference angle is going to be about 67.5 degrees. However, notice that everything has been in radians here. So let's go ahead and let's do that in radians. So to get the exact same answer in radians, just make sure that you change your calculator mode to radians, and you're going to get 1.18. And again, that's in radians. So therefore, your complex number is now equal to, let me erase this to give myself some room, the modulus, which is 5 root 3, times the cosine of theta, which is 1.18, plus I sine of 1.18. Actually, no, that's not. That's the reference angle. I never did find the actual angle. So let's take that 1.18 off. So 1.18 is our reference angle. So our reference angle is the first quadrant angle right here. So in order to find our actual angle, which needs to be a third quadrant angle, I'm glad we had this discussion. We need a third quadrant angle, which is going to be 180 plus that reference angle. Or since we're dealing with 180, instead of 180, it's going to be pi plus that reference angle. So pi plus 1.18, 3.14 time or plus 1.18, which would be 4.32. So our actual angle will be 4.32 here and 4.32 here. Simply use your reference angle to find that. Now, here, 67.5, had you used this, you would have done 180 plus 67.5, which would be 247.5. So you can write this in radians or you can write it in degrees. So let's go ahead and try to graph that. 4.32 radians, now that's going to be a little bit tough. So because a lot of people, how do I know where that falls around 3.14, and you'd have to type all these in. So what I'm going to use to graph it is going to be this 180 plus 67.5, which again was 247.5. So if this was 180 degrees and this is 270, I know that, let's see, I've got 1, 2, 3, 4, 5, 6 tick marks there. So that means that each tick mark is going to count 15 degrees. So this would be like 195. This would be 210 and 225 and so on and so forth. Well, I'm looking for 247. So this would be 240. This would be 255. So I'm going to be somewhere between 240 and 255. 247 is going to be nearly right in between those two. And then I need to go out a radius of 8.7. Each tick mark counts 2, so I'm going to go out 2, 4, 6, 8, nearly 9. So I'm going to be somewhere, and this is not exact, but I'm going to be somewhere right around in there. Okay, starting with number 13, we're actually going to convert it the other direction. Now, this is so much easier because now we're just pretty much simplifying. The cosine of 3 pi over 4 and the sine of 3 pi over 4 in parentheses. Well, first off, 3 pi over 4, we're talking about a 135 degree angle. So let's just clean that up. The cosine of 135, that's a second quadrant angle, so cosine will be negative. The reference angle is going to be 45 degrees, so the cosine of 45, root 2 over 2, plus I times the sine of 135, sine in second quadrant is positive. The sine, and so we're going to put a positive there. The reference angle is 45, sine of 45 is root 2 over 2. So now just distribute 8 times negative root 2 over 2. You're going to get negative 4 root 2 because the 2 and 8 cancel. Plus I times 8 times root 2 over 2. The 8 and 2 cancels and leaves you with 4 root 2. And that's it. So negative 4 root 2 plus I times 4 root 2. And here you could write that as 4I root 2. I just don't like you to write it as 4 root 2I. Because a lot of times that I will get trapped up under that square root symbol and it doesn't look right. So either one of those would be fine. Second one, 2 pi over 3, that's 120 degrees. So you're in the second quadrant. The reference angle would be a 60 degree angle. So let's clean this up. The cosine of a second quadrant angle will be negative. The cosine of 60, which is your reference angle, would be a half, plus I times the sine of a second quadrant will be positive. The sine of 60 is root 3 over 2. When you distribute the 2, actually the bottoms cancel and leaves you with negative 1 plus I root 3. And that's it. So you went from, again, this would be a polar form to complex form, or your normal form. 11 pi over 6, that is a 330 degree angle. So that means you're in quadrant 4. Your reference angle would be a 30. So now let's clean it up. You have 4 root 3 times. The cosine of a fourth quadrant angle will be positive. The cosine of 30, which is your reference angle, would be root 3 over 2. Plus I times. The sine of a fourth quadrant angle will be negative. The sine of a 30 degree reference angle is 1/2. Now let's distribute. 4 root 3 times root 3 over 2. When you do 4 times root 3 times root 3, it gives you 4 times 3, which is 12. So that'd be 12 over 2, or just 6. Plus, the second part actually is going to be a minus because you have a negative over there. You're going to do 4 root 3 times negative 1/2, which would be a negative 4 root 3 over 2. And you can put the I in second now because you can actually put it next to your fraction bar. And it's not going to get trapped up under that square root. So there you go. And I did forget to simplify that. The 4 and the 2 reduces. 6 minus, and then when you reduce the 4 over 2, it gives you a 2 and a 1. So that'd be 2, and I like the I in front of the square root. So 2I root 3 or I times 2 root 3. Okay, and the last one, the 3 pi over 2, that's going to be 270 degrees, which is a quadrantal angle. So your reference angle is going to be 90. So you have 5 times the cosine of 270 is going to be 0, plus the sine of 270 is going to be negative 1. So that's going to be I times negative 1. So 5 times 0 is going to be 0. You don't even have to put it. 5 times negative 1 will be negative 5i. So again, that is a quadrantal angle, negative 5i. If you were to look at it on the real imaginary axis, would be down here at negative 5. And you can see that this would have an angle of 270 degrees, and it does have a radius indeed of 5.